I'll slowly introduce you as people filter in. Yeah, so it's my pleasure to introduce Kevin Daniels to give us a fleet seminar today. So Kevin got his PhD from the University of Southern California.
Oh,
He
South
did
Carolina.
oh, did I say South Carolina?
Yeah.
How did I? I'm not awake this morning yet.
Oh no, you're fine.
South Carolina, and did a postdoc at Naval Research Lab where I first met him working with Kurt Gaskell and others on graphene, and so we've collaborated a little bit, and he's now at the University of Maryland, where I used to work some time ago. And he's going to talk to us today about building next generation devices with graphene.
Yeah, thank you very much for the introduction, Michael. It's a pleasure to be here. I know I'm talking to y'all in the past here in Tuesday while y'all are in Wednesday. But yeah, I mean, in the interest of time, let me go ahead and hop in. As the title suggests, we have a lab that is truly built on the back of epitaxial graphene. And a lot of the things I'm going to show in this presentation will just kind of illuminate just why we are so interested in the material in just terms of a lot of the physical phenomenon that will enable us to do some really interesting devices. So this is Maryland's campus. The building here on the right is the Institute for Research in Electronics and Applied Physics, where part of my lab is now, where we do a lot of material growth. And nothing, of course, would be possible from anything of these things I'm showing without the wonderful people in the pictures below, who really are integral in just about everything we do in the lab. And this is just a picture of our 3-chamber chemical vapor deposition system that we typically grow transition metal oxides and transition metal dichalcogenides, as well as condo insulator materials for quantum based devices. And so just kind of going through just everything that we do in the lab. As you see it, we cover a lot of ground. We definitely suffer from, it's like, ooh, that's really shiny physics, let's go do that. And we stretch ourselves a little too thin. But I think we're, going in the right direction in a lot of topics. But really, we mainly focus on material synthesis, and we take those materials and we try to do, really whatever the material strength is. And you'll see there's a lot of strengths in terms of epitaxial graphene. And there's so many topics that I would love to talk about today if we had 4 or 5 hours to go through everything. But in the interest of time, I'm going to try to stick to just a few topics, just kind of covering graphene, history a little bit, epitaxial graphene as a whole, quasi-freestanding epitaxial graphene, which is really the basis behind this talk. We'll talk about graphene-based optics, so THz detection and devices, and then electron emission for soft X-rays that we're currently working on. And then I'll end with some of our pathogen biomedical devices, which are really applicable to kind of our shared experience with COVID. So like I said, yeah, here's the overview of sort of what we're talking about today. And really, we're going to focus a lot on the graphene-based devices, as opposed to some of the transition metal oxide or dichalcogenide or condo insulator work that a good chunk of the lab is working on currently. So just a brief history of graphene. Novoselov and Geim isolated a single layer of graphite to form graphene using Scotch tape in 2004. Legions of grad students peeling and sticking these single flakes of graphene and showing just really interesting properties of the material. Geim is also I think the only person that actually has Ig Nobel for making a frog levitate due to diamagnetic levitation of water. And then kind of going, around the same time in 2004, Berger and Dahir at Georgia Tech, they demonstrated epitaxial graphene from the thermal decomposition of silicon carbide. And then from there, we have the electrical characterization, looking at room temperature quantum Hall effect, demonstrated in graphene in 2007. And then the main form of graphene that most people handle today, which is this large area graphene established on copper foil. Now you can get roll-to-roll transfer of the material to whatever size substrate, 6-inch wafers if you so desire. But there is, certain drawbacks, pros and cons to each. And so exfoliated graphene and CVD graphene, of course, very cheap. You can get for, CVD graphene, very large area, low cost. But then you start getting into really poor yields, small areas, small grain sizes. And so the remainder of the talk really going to be talking about epitaxial graphene. So we get single crystal graphene, very easy to process. It's completely CMOS compatible. But the biggest issues are the cost of silicon carbide, which luckily for us the costs are being driven down by the power electronics industry for electric vehicles. So it's been helping us out a lot in terms of the cost of a wafer. But like I'll talk about in a second, carrier scattering from the silicon carbide is an issue. And so, here we have graphene, really the first two-dimensional material, really exceptional properties, high electrical conductivity, high room temperature mobility, high surface area, quasi-ballistic transport of carriers, high current capacity, and very low noise. And that really is to our benefit, as I'll show in some of the applications we've done. Is extremely sensitive to the environment. So every atom is exposed to the surface. We get less than 1 part per billion limit of detection, high sensitivity, or sensitivity and very poor selectivity. So if we have a molecule land on it, whether it's electron giving or electron taking, you will have some change in your carrier concentration. So in this case, going more N-type. But it's important to note that these are weakly attached molecules. They are not covalently bonding to the material. You do get changes in carrier concentration, but the material stays highly conductive. The conductivity of graphene are dependent entirely on these pi orbitals that stick out of the material, not the covalent bonds that are holding the material together. Anyone who's processed graphene knows it does not like to stick to things. So, putting down oxides, putting down metals can be very, very challenging. And of course, there's an entire family of other 2D materials that have kind of spawned from, this first demonstration of graphene. So of course, we have 2D chalcogenides. So we have our dichalcogenides. We have a lot of different materials in that area, our MXenes, and of course, our 2D oxides. And so it really is a wealth of different materials that kind of have spawned from this, and as well as tons and tons of heterostructures. And we're very much in that mix as well. We look at a lot of 2D oxide coupled to graphene for our gas sensors, as well as 2D dichalcogenides coupled with our topological materials for spintronics. And so kind of going back into the epitaxial graphene. So when I was a postdoc at NRL from 2014 to 2017, this is the reactor I ran just about every single day. The chamber to the right is used for growing silicon carbide epi. The chamber to the left is for growing epitaxial graphene. And how that works is pretty much everything is made out of graphite. And so we have our susceptor sealing, which is made out of graphite. We have graphite foam insulation, which is, of course, a little bit more porous graphite foam. Inside, we have a susceptor bottom made of graphite, and then we have a rotating platter here. And the reason why everything is made of graphite is because of our heating. So we do inductive heating with the system to induce eddy currents into our graphite in order to heat it up. And we get pretty high temperature uniformity around plus or minus 1 to 2 degrees C across an entire 4-inch wafer. So it is extremely, extremely tight temperature tolerances because of how we're really growing our material, right? It's entirely through thermal decomposition. Silicon and carbon have different vapor pressures, so the silicon desorbs off, the carbon stays behind, restructuring itself into really nice single crystal graphene. And of course, if you're growing on a silicon face, there are limits. Typically, if you're growing on carbon face, you're getting, many layers, 4, 5, 6 layers. On the silicon face, because you do have, your carbon that is forming on the surface, your silicon really has a difficult time escaping. And so really, in terms of growth, most of your growth is not going to happen through your 0, 0, 0, 1 plane, but your 1, 1, 2 bar 0, 1, 1, 1 bar 0, 0 direction. So your A plane and M plane. And so what this really equates to is step flow mediated growth, where your silicon is desorbing there, and that's really where your graphene growth begins, as opposed to defect mediated growth that you typically see on the carbon face or the opposite side of your crystal. Okay, so one of the biggest issues, however, with growing on the silicon face is contending with the 6-3 buffer layer. And so the 6-3 buffer layer is simply just a carbon layer that is formed when you're desorbing your silicon, and that is covalently bound to your silicon carbide. And what that causes is tons of phonon scattering. And your phonons of your graphene are tied to the phonons of your silicon carbide. And so you can see here, our mobilities are nowhere near, the proposed, or the theoretical 100,000 centimeters squared per volt second. It's just not there. And mainly due to this electron-phonon coupling that we have. And one thing that's not shown here is that you do have pretty high temperature dependence. And so if you heat up the material, your carrier mobility will go down pretty quickly. If you cool it down, it will go up pretty quickly. And the material is N-type. And so the question is okay, well, can we passivate these silicon dangling bonds in order to release this carbon layer here? And can we, remove this electron-phonon coupling between the two materials? And the answer is yes, we can. So by introducing, close to atmosphere hydrogen at around 1050 C, varying the time, 60 minutes, generally optimal, you can actually passivate these silicon dangling bonds. You can release this layer, forming these really nice graphene layers. And the mobility goes up by, 4 times roughly. And so when this data was taken, we're getting around 4,000. Now, folks at NRL are getting around 5,000 centimeters squared per volt second. And one of the things to note here is that compared to this area here, where you have this buffer layer, and you have this 2 layers here, with quasi-freestanding, you're releasing this buffer layer. So now you have a pretty uniform 2-layer growth here. So you really get optimally 2 layers of material when you intercalate monolayer graphene. Interestingly, you get this high sheet carrier concentration of 10 to the 13. And as you can see, it doesn't really matter what the mobility is, it's practically unchanging. And this is really, really useful for plasmonics, as I'm going to show in a second. And you also get this order of magnitude drop in sheet resistance. So it really is a very, very conductive film, really, really high uniformity, which is also helpful for plasmonics. And so we can look here at AFM. So we have our surface roughness, we have our phase, and we have SEM images as well as XPS, and everything kind of points to improved surface uniformity. This change in contrast in our SEM lets us know, like, okay, we've released from the silicon carbide, and we're actually getting some charging, because we don't really have the insulating silicon carbide to kind of soak everything up. And we get the splitting of our C1s peaks, showing that, instead of us having this buffer layer here, and the distance between our graphene peak here and our silicon carbide bulk, we have the splitting, and we remove our buffer layer peak as a result. And then we can actually look at Raman mapping. So this is mapping looking at the 2D full of half max peak, which you can attribute the full of half max to number of layers. And so in this case, around 30 to 35, we generally have 1 layer. You know, in this green yellow range is generally 2 layers, and then the red range is 3 layers. As shown here, this is taking one sample and then intercalating it after the fact. So we've actually gone from 600 centimeters squared per volt second all the way to close to 4,000. And you can see the surface uniformity has improved tremendously. And we can actually look at the Raman, and you can see even the Raman peak intensity is much higher because we've separated ourselves from the silicon carbide substrate. And so all of this is to say we have a very, very nice material to kind of play around with. And there's some really interesting physics that comes about by releasing it from the silicon carbide and having it quasi-freestanding. Okay, so all of that to say that one of the really interesting things that we're able to show compared to using just plain epitaxial graphene is a narrowing of our THz plasmonic resonance using quasi-freestanding epitaxial graphene over just bare epitaxial graphene, or what people have demonstrated with CVD graphene, or even CVD graphene sandwiched between hexagonal boron nitride. And so one of the interesting things about graphene is it's one of the very few materials that really interact meaningfully going down into the near to mid-range to far IR going into the terahertz regime. Mainly because of it pretty much just being a semi-metal, right? It's a very small band gap, if no band gap, depending on the graphene you have. And graphene surface plasmons, these are these tightly localized electrons oscillating in collective motion. And this happens when you hit it with an incident electromagnetic wave. And so, you know, what we do is we take these kind of micron scaled graphene structures, and we're able to confine these oscillations and producing plasmons or plasmon resonances in this terahertz range. And so one of the things is, okay, well, why are we interested in THz detection? Well, really, it's not very many materials, like I said, interact with it. And so typically you have cryogenically cooled superconductors or bolometers. These are expensive and cumbersome simply because you have to have some mechanism of cooling them down. Thermal sensing elements are cheaper, but the sampling rate is, you know, at most 400 hertz, and they generally are much, you know, lower, going down to 10 hertz. And so they're really too slow for rapid detection. And so, you know, there's a number of things that terahertz radiation is good for in terms of healthcare, quality control, even evaluating cables or hardware, you know, identifying cancerous cells over non-cancerous cells. And this is mainly because of how terahertz radiation interacts with biological samples. And so things that you can pick up are, you know, various hydrogen bonding, molecular vibration, rotation, and any kind of van der Waals kind of structures that you have there using this terahertz radiation. And so this is kind of where graphene comes in, you know, because it is a semi-metal, and, you know, we can operate this at room temperature. Is ideal for rapid detection because instead of using, you know, kind of a bolometer effect, we're using a plasmonic effect. And one of the benefits of epitaxial graphene is we're getting single crystal, very uniform material across an entire wafer scale, rather than flakes that you would typically get with, you know, exfoliated films, or even if we're talking about doing transferred CVD material. Now we're talking about materials with very small grain sizes, which can affect plasmon resonance. And so this is a graph that was put together by a colleague, Mehdi Jadidi, where he was able to plot this out. Basically, this is plasmon resonance as a function of carrier mobility. So when they were using as-grown graphene, you notice the mobility was around 1,000, so you're getting pretty wide resonances. But as you increase the mobility going up to the theoretical 100,000, you get much, much narrower plasmon resonances. So the idea was, okay, well, we have this material with 4 times better carrier mobility. You know, approaching 5,000, we see the same effect. And so we have our structure here. We have some contacts here for gating, and we're really just making these ribbons. And the reason why we want to make these ribbons is because there are really 2 factors that can control what your plasmon resonance peak is. One of them is your carrier concentration. And so going from, you know, 10 to the 11 down to, you know, up to 10 to 13. You can have huge shifts in your plasmon resonances, all the way to 8 terahertz, as shown here. And you can control it by actually confining your plasmon resonances by patterning it. And so because all of our quasi-freestanding epitaxial graphene samples are 10 to the 13, we can focus on just patterning to kind of control this, as well as gating. And we can actually control this end through gating as well. So this is our setup here. We have, this is a much simplified equation, just saying that our carrier concentration compared to our plasmon resonance frequency goes to the power of 1/4, and then the width of our ribbons goes to the -1/2. And so the two things that we can control, because again our carrier concentration is set, are through carrier concentrations through gating, and then changing the duty cycle or the width of our graphene. And our measurement system, ironically enough, uses 2 bolometers. We have our mercury source lamp, and we have 2 4K silicon composite bolometers on either side, one on transmitted, one on the reflected side. And then we have a polarizer used in the beam path to pass polarized polarization perpendicular to the graphene strips. And the THz beam is illuminated on the backside of the sample. And we have this really cool copper aperture here that we're shining through. So we would first, grab just a bare silicon sample and do this test, and then we'll have our silicon carbide sample, and then we would do a silicon carbide sample with our structures, our graphene structures. And so the very first thing we looked at is an unpatterned graphene sample. So basically just looking at the Drude response, and we were able to fit this with a single Drude model. Which is pretty great, and we were able to show really narrow plasmon resonances of around 30 wave numbers. This is with a sample with a carrier mobility of around 3,200, and it really showed little dependence on polarization. It was a little bit larger perpendicular to the steps, which of course are scattering sites in graphene. Now, we patterned these samples in a few different configurations. Unfortunately, some of that is blocked off. I noticed these structures are down here are 0.75 microns with a pitch of 1.5 microns. But as you can see, we're able to shift going from around, I think it's like 1.7 terahertz all the way to around 5 terahertz. Simply by changing the period and the width and the period of our grading. And so one of the other things we wanted to show was not just the width, but actually gating. Can we shift our plasmon resonance through gating? And so this is a non-intercalated sample here to the left. As you can see, the resonances are pretty wide. Mainly because of the lowered carrier mobility, as well as the scattering associated with it being coupled to the silicon carbide. But in our intercalated case, as you can see, we get really narrow plasmon resonances. So these are around 40 or 50, again, a consequence of the patterning. And we're able to gate it from 10 to the 13 going down to about 5 times 10 to the 12. And we're able to cover a good bit of ground through just, very, very simple. This is using electrolytic gating in this case. And so, we're able to demonstrate not only that, yes, we can improve this resonance through improving the carrier mobility, but also through gating, we're able to shift this plasmon resonance, pretty much to the letter of what our equations are telling us. Okay. So that's one aspect of just, looking at, the plasmonics and terahertz detection using epitaxial graphene. We want to shift focus a little bit. And so the previous work was the work that I did at NRL. Now I'm shifting to a little bit of focus to the stuff that we're working on in my lab. My lab is has become very health-centered. And that this work is really focused on generating soft X-rays for medical diagnostics. And we do biological detection, and we do gas-based detection for human breath. So really very bio-focused. This work is the work of Mr. Daniel Lewis, who is defending this summer, and a lot of the supplementary kind of efforts by my students Brendan Jordan and Michael Pedowitz in this work. And so what kind of sent us down this path was talking with the School of Dentistry at Maryland, and they were interested in generating X-rays to try to do X-rays for teeth without completely flooding them out with X-rays. And for instance, if someone has a filling and you try to do an X-ray near that filling, it's very, very difficult. You actually those regions will actually light up and block any kind of vision you have on, let's say you have a cavity nearby. And so the idea was, okay, well, can we generate X-rays on a much smaller scale, be able to control the dosage a little bit better, to be able to have detection of, let's say, cavities or whatever small thing you're trying to see, without flooding the entire area with X-rays. And so we're really interested in these kind of soft X-ray to these tender X-ray range, so around 100 electron volts to around 10 kiloelectron volts, at least for now. And really, again, it kind of goes into this medical radiology where you want to balance radiation dose with useful image generation. In 2006, for instance, all medical, or about 50% of all radiation was attributed to medical irradiation. And so, just kind of showing why we're making electron sources, because generally all X-ray generations are driven by some electron source. And so your X-ray photons are generated when you have a beam of electrons, as shown here, collide with some target, emitting electrons or X-rays, excuse me, as a result. And so there's a few different types. You have a reflection anode, which is generally the type of anode used for X-ray generation. And then you also have interaction anodes, which instead of reflecting your X-rays off, you're depending on transmission of your X-rays after colliding with your electrons. Both of these, however, require a vacuum enclosure. And so the sort of the idea behind our system that I'll show in a second is, can we remove the vacuum? And so what kind of sent us down this path with graphene was this phenomenon called phonon-assisted electron emission, where people have seen this in suspended graphene nanoribbons, and they were showing that you can get electron emission out at temperatures and electric fields far too low for either thermionic or field emission. So most of our electron emission we can think of is thermionic, where you have, let's say, some tungsten filament, you're heating it up to a couple of thousand Kelvin, and you're really boiling off electrons and giving them the energy to escape. So essentially surmounting this vacuum gap and hitting the vacuum level and allowing your electrons to escape. Of course, there's field emission, where now you have, let's say, some very, very sharp point, and you're applying a really high electric field to allow your electrons to tunnel out. And so having something that is a lot, doesn't require extreme fields, doesn't require, very extreme heats, that was sort of the idea. And so, as I said before, electron emission from these graphene nanoribbons was, demonstrated and shown that, okay, well, you can actually get emission out without really having to put much effort in terms of temperature or field. And the basic consensus was like, okay, you're getting emission currents with no elevated temperatures and fields far too weak to be able to get that kind of emission out. And then people subsequently looked and did experiments with unzipped carbon nanotubes, CVD flakes, all of these requiring very extensive fabrication procedures and equipment to actually suspend these flakes. And it's very fragile and really not easily reproducible. And that's something that's, we try to do in my lab, is make sure that we're building things that, have really high repeatability. And so the idea was, okay, well, if these are just freestanding graphene flakes, our graphene is quasi-freestanding, can we get the same kind of emission with very little energy put into the system. And so here's sort of the design of our initial test. We decided to do a lot of these different patterns simply because we really weren't sure where points of emission were coming from. Simply because there was very conflicting things in the literature as far as where these electrons are being emitted from. Some said that, hey, you just need to have the ribbon suspended. Others were saying, okay, well, you need to have some kind of points, and these points are the sources of emission. Very similar to what you would get with field emission source. And so we did all these, really kind of patterns trying to, have very many points that could be used for emission. More dangling bonds, the better, as example of the serpentine shape here, but also maintaining the amount of graphene that is there within the ribbon. So there was a lot of geometry considerations taken to make sure that all of these devices were generally the same, with the exception of their geometry. And so this is just a 3D mock-up of our device. So we have, for example, one ribbon here. We have a thermocouple kind of going in here just for us to monitor the temperature of our device. And so this is our testing setup here. We just have a copper gold plate sitting on top of our package here. And we have a potential applied to our graphene ribbons. And we have an accelerating field between this plate here, and our top plate for our accelerating field. And all of this was done in a vacuum chamber. Again, not very high vacuum, around 30 millitorr. So, just with a roughing pump. So going nowhere near what you would typically see in like a E-beam system, like 10 to the -6. We're not getting anywhere close to that. Okay. And so for our first test, we just applied a field, and we applied a voltage across our devices, and basically allowed them to self-joule heat. And so you can see here, we pretty much have no emission, very little emission, if any. And then we start seeing it take off. And interestingly enough, all of these devices tended to take off in terms of emission around a little less than 150 degrees C. And so this is something that's repeated through all of our devices. That seems to be the turn-on temperature. So there does seem to be at least a little bit of a temperature requirement compared to the truly suspended samples. And we also noticed that was a shape correlation that showed up, repeated tests over and over and over again, where the zigzag shape was much, much better than rectangular, then the serpentine, then the square wave, letting us know that the more sharp points that we have, the better emission that we get. So some of the tests that Daniel is doing now for his next paper have much sharper pitch and many more points, and he's been able to see higher emission from those devices. Another test, which of course is very interesting or useful for X-ray emission, is he varied the accelerating field and was able to show that his electron emission was directly proportional to his accelerating field. And he was able to show this for all of his devices. And again, the zigzag shape was the better device. And then he was able to show through external heating. So we were saying, okay, well, all of our devices are self-joule heating. What if we provided the heat? What kind of emission will we get out? And interestingly enough, when we did use our external heater to heat it up to around 150 C, we got even more emission out of our devices that we didn't have to supply ourselves. And so for our devices in the future, I think that's what we would end up going with, is just instead of having self-joule heating, just have an external heater that we can optimize our emission current out of our devices. And then this was a really interesting test. So what Daniel did was he had one of his zigzag tests. He brought it up to the maximum sustained temperature via the external heater. And so he was able to show So here's our temperature here. You can see it go to 150, 150, and you see the emission current go up. And then he switched off the external heater, still applying his input voltage, and immediately self-Joule heating took over, and he saw a drop in his emission current as a result. And so in terms of max electron fluence, and in terms of this best device here, so he's getting around 1.33 times 10 to the 15 per centimeter square. So he's getting, right up there where he needs to be in order to get meaningful electrons to collide with a target. And so really the main takeaways here is that our elevated temperatures lead to elevated phonon density, and then that allows for us to have emission out because we have more phonons to kick out these electrons. We get higher performing morphology or performance out of a morphology that is zigzag shape. So we get, is possibly due to this, having more numerous unterminated edges versus the other shapes. And then this external heating versus the self-Joule heating that we're currently exploring now. One of the things that we're really interested in is taking hexagonal boron nitride and laying it on top. That could possibly allow us to put a transmission anode on top and actually make a transmission X-ray source without having to need the vacuum. Really, the most important thing that we're currently investigating is that can the device handle the electric fields that we would need to collide with the anode at that distance. Okay, so the very last thing I wanted to cover was this lattice strain induced biosensing that we've noticed from our quasi-freestanding epitaxial graphene. So this is work that was done by now Assistant Professor Saram Kim, who is at Texas A&M now, who started in January. He was a postdoc with me for three years. Yeah, 3 years. And Michael Pedowitz has taken over a lot of the work, and a lot of the theory and how the device worked was theorized and formulated by Michael. And so in the interest of time, I think I might skip over a little bit of these things. I think everyone here on the call has had a PCR test, has had a rapid antigen test. They have their drawbacks. PCR, of course, takes a while to get your results. And you have to have really expensive instrumentation, trained personnel, professionals, in order to be able to do these tests. And rapid antigen test is really high incidence of false negatives to the poor sensitivity. You have to be pretty sick in order to turn up positive on a rapid test. And so, there is, other than vaccines being, very, very effective, there really is, not very good screening for pathogens, in order to be able to contain a pandemic. And so, the question is that can we detect viral antigens in real time using our quasi-freestanding epitaxial graphene? And so when we decided to start doing this, I, had said like, hey, a lot of people have done graphene-based biosensors. What makes, our platform really any different from theirs? And my postdoc Saram, he was like, no, let's try it, because at the time we had done gas sensors that had shown response and recovery times in seconds, and so yeah, the rest is kind of history. And we fabricated these devices. So very, very simple fabrication process. You have a graphene synthesis. We etch the edges away in order to secure our tie gold contacts. As I said, graphene doesn't like to stick to things. And then we put a crosslinker. This is a poly-L-lysine crosslinker that forms covalently with the antibodies that we put down and non-covalently with the graphene. Because as I said before, if you form covalent bonds with graphene, you kill the conductivity, you kill the mobility almost immediately. So we didn't want to do that. And so really we're kind of interacting with the pi bonds meaningfully with each binding. And so we got some really interesting results. We got direct electrical detection. This is a very, very simple device structure. It's 4 contacts, but we really only need 2. because it's really just a resistor. We don't need to make a field effect transistor, and I'll show why in a few slides. But we were able to detect all the way down to an attogram per milliliter. This is really, really important because we are using a microliter of solution. And that equates to roughly 4 spike proteins of a virus. And so our limit of detection really is a single copy to less than a single copy of SARS-CoV-2. And we're able to go down from 10 to the minus 18 attogram range all the way to a microgram. And so really we're spanning 12 orders of magnitude in detection range with this sensor. And a response time is super, super fast. Generally less than 4 seconds, we get a response. Most of the time we get a response in less than a second. And so, as I said, we're getting down to an attogram range. We tested our sensor with just bare graphene. So this is pure graphene, and we put down 100 nanogram per milliliter on top, and we only got a response of 6.2%. Putting down an attogram, so many, many orders of magnitude less, and we get a response of 30%. And so we know that this is an effect of binding, not just some transfer of ions that are in our solution. And as you can see, to an attogram per milliliter, we get a really, really fast response. So again, in a second to less than a second, we get a pretty fast response, letting someone know it's like, okay, well, you possibly have the virus, well, not possibly, but do have the virus. We have to say possibly because this device is not FDA approved. And so, what's the explanation of this really unprecedented limit of detection? Because if we're talking about 4 bindings, we are not talking. We're only talking about 4 electrons being generated, which would not cause our device to change conductivity to change, 30%. So what is happening? And so this is our structure here. We have our silicon carbide. Silicon bonds are passivated with hydrogen, and we have our bilayer graphene on top. And so we looked at the in-plane vibrational modes, or G peaks, was sitting at 1595. Then we put down our poly-lysine, which is filled with amine groups, and that goes to 1589. We put down our antibody, it goes to 1586. And then when we put down our virus, so this is again an attogram, it shifts all the way to 1584. And so it doesn't seem like a very significant change, except that we're only having around 4 bindings in our material. And so what we believe is happening is that we have a strain effect. And so we have our Fermi energy here. As a binding happens, we have an opposing polarization field between our poly-lysine and our silicon carbide, because our hydrogen terminated silicon carbon or silicon bonds. This is one reason why our graphene is heavily p-type, because it is dragging all the electrons from our material down. And so when we put down our poly-lysine, it's having an opposing polarization field. And so this is a strain effect being applied to our graphene here. And when we have a binding, then we have this kind of competing a strain effect that causes a decent amount of strain in our graphene, resulting in this changing in carrier concentration. And we compared this to just really, really high quality chemical vapor deposited graphene. And after putting down our antigen, we didn't see an effect. And so we believe the sensor didn't work because in CVD graphene is limited to charge transfer only. So this is looking at femtogram per milliliter kind of range. So many, many bindings happening. Okay, and so kind of a little bit further explanation to the strain effect. And so when we grow graphene, we have 2 competing strain effects. The tensile strain due to the larger lattice constant of silicon carbide, and then a compressive strain due to the larger thermal expansion coefficient of silicon carbide. So this leads to a net compressive strain of 0.5%. And then when we intercalate it, it relaxes to around 0.3% because of this decoupling of our buffer layer. And so, if we look here at our Dirac cone here, so we have our biaxial strain is there that can modulate our Fermi velocity of our structure. And so this strain can lead to narrowing or widening of our cone. So this is unstrained graphene, compressive strain, and tensile strain. And you can kind of see how our Fermi energy can shift with various strain effects. And then the other explanation is this doping of our material. So we have a polarization field caused by our polar silicon hydrogen bonds. We have free electrons and our pi network. They are trapped here below our graphene. And then this is why our graphene takes on this net carrier concentration of holes, very similar to gating. And so even though I said before we did not have a field effect transistor, we have a field effect transistor. It just happens to be built into the material. And so whenever we put this additional crosslinker, so this poly-L-lysine on top, we have two effects happening. We have this deprotonated amines form this cation pi interactions. So this is an opposing polarization field to the silicon carbide, and the whole doping of the graphene is reduced as a result. And then we have these positive amine groups repelling the holes like carbon atoms. So we have a tensile strain that's created, and this is opposes the compressive strain in the graphene. So we have this huge shift in our material from 1595 to 1589. And now you're thinking, so why didn't that happen as significantly in the CVD graphene case? Well, if you think of the CVD graphene case, the grain sizes are actually pretty small, right? They're in the order of 10, 20, 30, 40 microns. And so in terms of long range pi network, you don't have it. And any kind of strain that you generate is very local to that grain. And so, once you get to the grain boundary, that strain effect is lost. This is something that doesn't happen for epitaxial graphene because our grain sizes are on the order of millimeters, and essentially across our entire sample. And so what we're proposing is two sensing mechanisms. One where we have a small spike protein concentration. This causes deprotonation. It removes tensile strain caused by the cation pi interaction. And then we have a propagation of uniaxial non-uniform strain altering this cation pi bonds. And this causes a shift in the Fermi energy that we can electrically transduce. And then when we get into higher concentrations, of course, our typical spike, our typical charge transfer that everyone has observed. And then how we can kind of look at this is that we see a drop in our significance, our figure significance. So we did a t-test on each one of these points and noticed there was a breaking significance around 10 to the 15, going to 10 to the minus 12. So this is where our people would typically start being able to detect bindings with a typical graphene field effect transistor, and this is where we're kind of able to detect with our sensor. And so this breaking significance is significant because this is all controlled by strain. This is all controlled by typical charge transfer. Where was I? Okay. And so, of course, this is all just, in lab tests with isolated antigen and isolated antibodies. So the next step was to test with clinical samples. And so this is definitely thanks to Professor Don Milton at the University of Maryland. He let us into his lab and allowed us to test our sensor with collected samples that he had taken. So swab samples, aerosol breath samples, and saliva samples. And as you can see, we're able to detect down to 60 copies per milliliter, as opposed to traditionally PCR is able to detect 100 copies. And we're able to get pretty high resolution or high sensitivity and quantitatively be able to detect patient samples that are positive as opposed to negatives where we're not getting anywhere near above our noise threshold of 20% change. And it's faster and more sensitive than conventional tests. And all this is non-invasive, with the exception of the nasal swab. And so, of course, one of the next things we did was we looked at other seasonal coronaviruses. And we're able to show that in extreme concentration, so 10 to the 8 copies, 10 to the 6, 10 to the 7, 10 to the 8 for these seasonal coronaviruses, yes, we do see a response because the spike protein is very similar to SARS-CoV-2, but we never reached over the 20% threshold that we set. This is compared to just 60 copies of SARS-CoV-2. We're getting responses higher than extreme copies of conventional ones. And so we can see here, so this is swab, aerosol, saliva, and then also we looked at one of the COVID variants, showing that we're able to get responses much higher than very extreme copies of these seasonal coronavirus. So we developed a very selective sensor as well. And so this is our prototype unit, much cheaper than our $20,000 potentiostat we use to test some of the other devices or sensors. But as shown here, variant positive, so 8,000 copies, 4,000 copies, it's able to transduce things no problem. Our sample size is extremely small, only a microliter compared to much larger volumes in other cases. And so I'm going to end it here with this video. And so this is detection of B117 variant. So here we have our sensor package. This is just a dip package here with our sensor wire bound. So here is Saram putting on a blank sample. As you can see, we have a pretty small response shown here, but then he's going to drop a patient sample, and then boom, immediately huge response. And so kind of going forward a little bit further. So as you can see, it saturates pretty quickly. But it definitely lets you know something is positive, very quickly as well. And then it will say, like here, saying like virus found to the poor soul who just was tested with our sensor. And so I'll end my talk here, just showing that we use graphene for a lot of things: emission detection, sensing. Even beyond what I've shown here, we do a lot of gas sensing work as well. We're currently funded by NSF for doing selective-based gas sensing using transition metal oxides with very large interlayer spacing to detect molecules by kinetic diameter. But yeah, so everything is pretty much kind of fueled by graphene. Here is our sponsors and collaborators. And we've just got a grant in for detection, converting our sensor for detection of influenza, which I should have added here. But again, thank you all for your time.
Thanks, Kevin. If anyone's got questions, just unmute yourself and fire away. I might not have any questions. Well, if there's no questions, guys, Kevin, look, thank you very much for your time today. It certainly opened my eyes to all the things you can do with graphene. Some things I had no idea about.
I'll just comment. It was a really cool talk. It's really nice to see those very sharp graphene plasmons and high mobility graphene. Finally, we worked on that for a while, so
we did, yeah.
Yeah, it's good to see them really pop up sharply, and that coronavirus detection is really cool. So great stuff.
Yeah, thank you very much.